Hey, BC Calculus, Mr. Ellinger here, and we're starting off Unit 8. 3 units to go, 8, 9, 10. 8 and 10 are both kind of big, so, it's like 3 units, but it's like, okay. All right, so let's go. So starting 8.1. So what is Chapter 8? Chapter 8 is applying integrals. We had the same thing with derivatives, where people were kind of like, when are we going to use these things? And then suddenly, we had all these applications of derivatives. So the same thing's going to happen with integrals, where we've been doing lots of techniques and ideas about them, and we've done some applications with diffie-qs, but now there's a lot more applications that we're going to see in Unit 8. So the first one, 8.1, is a very kind of standalone individual one called the average value of a function. So we've done average rates before. So for example, if an object moves along an axis, so I'm just getting it so it's moving in a line and I'm just in one dimension, with a position function that x of t equals t squared, what's the average velocity from t equals 1 to t equals 4? Now, in the past, it says, leaves you room here. You could work it out. But in the past, what we said was, okay, it's a position function, so the average velocity is going to be the average slope. So, I just need to do 4 squared minus 1 squared over 4 minus 1. And there's no units on this thing, so it's 15 over 3, which is 5, whatever the units are. So what's new? That's not new, that's old. So suppose I gave you the actual velocity function instead. I said, this is the velocity function, and I asked you what's the average velocity. So I'm not asking you what the average slope is for a given function. I'm asking you what the average y value is from a given function. So we know v of 1 is 1, we know that this function goes like this, and so we know this is velocity now, and we know at 1 it's 1, and we know at 4, not to scale, it's at 16. But what's the average velocity? And you can kind of think about it that it's traveling, like if you try to do it like a straight line kind of approach to it, it's traveling slower than that initially, than the straight line approach would suggest. So it's a little like, okay, this is a thing. So there's a formula for this, for finding the average y value of a function that you're given, rather than the average rate. Mean value theorem, that was average rate, and this is average value of a function itself. So here's how I like to think of it. So think about this velocity situation. Average velocity is change in position over change in time. Okay, here's my velocity. What's my change in position looking at this? And going back to the little bit of distance rate acceleration kind of stuff, velocity acceleration, is that we said, that the displacement is the area under the curve. That is my change in position. Rather than subtracting two positions, if I'm looking at position function, this area under the curve is the change in position for a velocity function. So, okay. Then, so for the change in position, I just need to find that area. And, I know how to do that. So the area is the integral from 1 to 4 of t squared dt. That's the area under the curve. But I need to divide that by the change in time, which is 3 units. And you've got it. Now, of course, you'd have to do this. You'd have to go, t cubed, 1/3, and then evaluate that from 1 to 4, still divided by 3. And so that's 4 cubed is 64/3. I know I could simplify it differently. Minus 1/3 over 3. So that's 63 over 3, which is 21 divided by 3, which is 7, I think. Right. And so we think about it, from 1 to 16, it's not right in the middle. The average would be 8.5 if you average 1 and 16. But we were traveling concave up here, and so we're going slower than a linear approach would be. And so therefore the average y value, the average velocity here, is a little bit slower than the straight line approach would say. And so the average velocity is 7. So the average velocity we travel right then, which is a little earlier than halfway through. Wait. I'm thinking about that. That's earlier or later. Doesn't matter. But square root of 7. Okay, I'm not going to worry about it. But it's actually, I think, a little bit later than 7, than average. Okay, doesn't matter. But regardless, the average y value I find by finding the area and then dividing it by the space. So here's the the interval. So here we can generalize. If you're given a function, then the average rate of change would be f of b minus f of a over b minus a. But the average value of f of t itself would be the integral, you gonna work for me? Yay. From a to b of f of t dt divided by b minus a. Because that is the change in position. So, for example, find the average value of cosine squared x over 0 to pi. You can use you'll need a calculator for this. I wanted to give you a little more practice right away on using your calculator to find area, because you need to be able to use integrals on that pretty confidently. So set it up and find the area. It's just doing the integral, but that integral you'll do on the calculator. And set it up at least, and then if you're having trouble with the calculator, I'll show you how to do it in just a second. Pause the video and do it yourself. Okay, so I'm going to get my calculator going, and so while I'm doing that, so this is going to be the integral. You still on with me? Come back, there we go, of cosine squared x dx from 0 to pi, and then divided by pi minus 0. And so that's 1 over pi times that integral. So now I'm going to do that on my calculator. And so doing stuff for stats there. And so the fastest way to do integrals, I mean, you can graph it and get the window and do all that. I like to do it just with math. And then you can see number 9 on all the different models. Number 9 is function integrate. So I'm going to integrate this thing. Now, if you're on an 83, you have to first enter your function, and then x, and then the bounds. But on here, it's backwards. I mean, well, it's normal, I guess, from 0 to pi, and then my function. And you have to put your function inside these parentheses. It has to be inside these parentheses. So I can't, write cosine x and then use these parentheses to square it. I have to put the whole thing inside. And correctly, so it's cosine of x I gotta hit x, all right, and close parentheses, close parentheses. Okay, let's try that again. Cosine of x, it keeps doing that. I'm okay on the calculator, I'm just having trouble on the computer. Okay, cosine of x, close the parentheses. Oh, that's why I'm running into trouble. Yeah, okay, I gotta do that. And now I need to square this whole thing, but I can't square it out here because the function has to be inside the parentheses. So I'm gonna have to put another parentheses in there and then scroll over. And insert another parentheses there. So cosine of x, close parentheses, squared. Notice how it doesn't let me type over this bound. This bound, it doesn't let me do anything with it. That's stuck there. So you have to put the function in. You could also put it in y equals, and then dx. And if you're doing 83, it's going to be the function, then x, and then the bounds. All right, here we go. And what's that area? That's the total area of cosine x from 0 to pi. And now it's divided by pi. Divided by pi. Think I know what the answer is. It's 1/2 on the nose. So it's 0.5, 1 over pi times 1.57. That's the area of this thing, and which equals exactly 1/2, because this is pi over 2. Now we don't know why, because we can't integrate this by hand right at this point, because we don't know how to integrate that thing. But we can use the calculator for it. Right? So that's the average value function. That's what 8.1 is about. That's it. I guess I'll say one more thing really fast about it, which is that one way you can think of it is you think about what's the area under the curve. That's all this stuff here. And so you're taking that area, which is a y value, or area is both, right? Area is both, y times x. And then you're dividing it by the x, and that's giving you what the average y is. So what this means is you're taking the area, and this is not to scale, and you're taking the area, and it's kind of like you're smushing it down. Like imagine the area, this shape here was made out of something a little thicker than pudding, something that would keep its structure if you let it go, but it's totally movable, like like cookie dough, maybe. Yeah, cookie dough, right? If it's cookie dough like that, it could hold its shape like that if it was a pretty firm cookie dough there, but you could still smush it. And so what it's like, what it's doing is it's taking this extra area here, and we're smushing this down and tamping this down until it creates a rectangle with the height of 7. I mean, that's what we're doing, is we're taking that area and dividing it by this, and so we're finding out what the average y value is, which is what would happen if you smushed it all down and made it one long piece. And that's a weird little aside that I always liked as a visual thing. All right, now we're going to take a quick look at position, velocity, acceleration, and this is the last time we're going to bring up position, velocity, and acceleration in the AB course. There's a little more in BC. So a rolling marble has an acceleration function of this. At t equals 1, the marble has a velocity of this, a position of this. Find the velocity and position functions for the marble. And pause the video, and you can do it yourself right now. Okay, I'm going to do it. So v of t is just the antiderivative of that thing. And so it's just going to be the integral of 8e to the 2t minus 2 minus 3t to the negative 1/2 dt. All that is multiplied by dt. So that's going to be, all right, so e to the something is e to the something, but I need to have the constant there. So that would be, so the 2 is going to be eaten up by the integral, so it's going to be 4e to the 2x minus 2. Yeah, and that goes to t to the 1/2, and then bring the reciprocal down, so it's minus 6. Derivative of that, checking it looks good, plus c. Right? Because it could have some initial velocity that we don't know, and so we have to factor that in. It says at t equals 1, the marble has a velocity of 6. So that's how I'm going to find my plus c. This is like my initial condition sort of thing, except it's at t equals 1. So 6 equals 4e to the t is 1. Sorry, I used x's. That should be t. And so e to the 0, ooh, like that, minus 6 times t to the 1/2, that's 1 to the 1/2, oh, love it, that's 1, plus c. So 12, I'm getting that c equals 8, I think. Add that over 12, subtract it over, yep. And so my velocity then is 4e to the 2t minus 2, ignore that minus there, minus 6t to the 1/2 plus 8. And now to find the position function, I can just integrate it again. P of t equals, now I'm integrating, I'm antiderivating again, but now I kind of know what I'm doing here, so I don't need to write the integral symbol, I don't think. The position is going to be 2e to the 2t minus 2. Take the derivative and see that it works and it gets you what we thought. And then, and that's t to the 3/2 now, but if I have to put a 2/3 in front, 12 over 3, so that's 4 minus, and then plus 8t plus another constant. You could mark that as c2 if you want. And now they told me at t equals 1, it's got a position of 11, so 11 equals 2, that's 1, minus 4, that's 1, plus 8 plus c, and so that's 10 minus 4 is 6, subtract it over. So that's giving me a position of 5. If I made any mistakes, I'm just trying to finish in time. And so the position function is 8e to the t minus 2 minus 4t to the 3/2 plus 8t plus 5. So you can just do antiderivatives to go from acceleration to velocity to position, but you need to have some kind of initial condition so that you can figure out what the constants are. All right. We'll have to take a look at this one in the next video. I'm only going to be able to record that, I think, on Saturday because I've got to go home now. And so we'll be recording this video on Saturday. So we'll see you then. You can check out this one. This big one is what's the difference between these different phrases, and we'll show you that next time. So what have we got so far? We've got average value of a function. That's one application of integrals. And now we're looking at position, velocity, acceleration, and how to use antiderivatives to go from acceleration backwards. We're going to be looking at what does the area represent, what's the difference between change in position and distance traveled, and then we'll be looking at a few other things. It'll be worth it. It'll be worth it. So another video coming out tomorrow. my time's up here. So take care, and hope you're having a great weekend. And we'll see you in just a little bit.